Well, good morning. This is a flipped version of lecture number 15 because I'm sorry I can't be with you for this, but hopefully by watching this you'll have caught up with most of the content that we would have covered and you'll have the time in the lecture to be able to get on with your own project, working with your partner there. So we're thinking here very much about virtual worlds, about 3D representations of objects, about simulation, and about computer modelling. We go back right to the start, well, not quite the start I suppose, but we go back to Piaget talking about this development of mental schema and how important the role of playing with objects is for that. And of course he was thinking about what we would call now the concrete operation of a child playing with building blocks or balls or whatever. But now we might think, for a child who's grown up surrounded by digital technology, that the virtual operation or the virtual manipulatives are just as powerful a tool for establishing those mental schema as playing with real-world physical toys ever were. That's not to say that there's anything wrong or we shouldn't include playing with the real-world objects alongside that. But think of all of the opportunities for play in realms which otherwise would have been absolutely impossible for a child to access, that if we make this move from the physical to the virtual, I think for a young child now that is something which is not too difficult a step to make. Papert, writing in Mindstorms, this was the chapter that I asked you to read, returns to this Piagetian idea of construction of knowledge, of building on existing mental structures, relate the new information to something which you already know. So we're thinking of the twin processes of accommodation and assimilation there. And how does a child go about learning physics? How does a child go about learning Newton's laws of motion, apart from through the direct experience of objects which obey those laws? I think Papert would argue that by moving onto the computer screen, by looking at those in Logo, not only do you get to play with the simulation, but at least there's the opportunity to look at the code on which they're based, and learning about the laws of physics, learning about something like Newtonian motion, through being able to model that yourself, through being able to look at how others have modelled that. That's a very powerful learning tool, I would have thought. So we have also there this notion about needing that there's more needed than just the seat of the pants direct experience. By conceptualizing, by capturing some aspects of how the world is in a computer model, and that's a very, as I say, very powerful learning experience. And the micro world is the opportunity, this sort of small Lego world in which the student, the pupil, has written their own scripts in Logo, their own programs in Scratch, if you will, to simulate at least one aspect of physical reality. Very powerful technique there too. And we had this back in the old edition of the National Curriculum. Douglas Adams, author of Hitchhiker's Guide to the Galaxy, writing in the prologue to the 1999 edition, about the difference between scientific method and what we do in computing. That when scientific method we take things apart to see how they work. With computer science we have the opportunity to put those building blocks together and to try putting them back together in a different way. You can simulate whole other realms of physics by just changing some of those laws, but the opportunity to create those programs, to create those models, those simulations, provides the opportunity to model complex interrelated processes, including life itself. And Adams saying this is a new age for discovery. And it is interesting to think of how computer science, how programming has transformed so many academic domains. You very rarely get the experience of that at school level, beyond particularly physics, I would suggest. But so many aspects of academic study now strongly influenced by advances in computer science and programming. I was at a seminar recently with colleagues over in the Humanities Department looking at exactly that. Some very interesting work going on there. And we have this, of course, in the new programme of study as well. The prologue, or the introduction to this, begins: high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. The creativity we know well. But notice the link between computational thinking and understanding the world. Computing has deep links with maths, with science, with design and technology, and the insights that it can provide into both natural and artificial systems is exactly in this territory. Of core of computing is computer science, in which pupils are taught the principles about how the systems work and how to put this knowledge to use. There are specific requirements down there in the programme of study. So, for instance, in Key Stage 1, that pupils should be taught to use logical reasoning to predict the behaviour of simple programs. Now, that's typically going to be interpreted in terms of their own programs on Bbots, on Scratch, perhaps. But you could also see it in terms of predicting the behaviour of a simple computer game. What's this game going to do? And playing a computer game typically involves making a prediction as what's going to happen, of trying to understand the algorithm that the programmer has coded into the game. How else can you play Angry Birds? And then, of course, designing and writing programs that accomplish specific goals up in Key Stage 2, including control, but also simulating physical systems, creating your own computer game which simulates at least part of how the world works. Or it doesn't need to be an interactive simulation, as you'll see in a little while's time. Why does this matter? Physics is really, really important. If we were there in the room, I'd ask you about your experience of learning physics at school, and you might care to blog about that. But any work over in the computer games world or in the visual effects industry is going to draw on a very, very solid understanding of physics. Remember this talk of the T-shaped individual. Yes, you have your strong core of computer programming, your broad T-shape there, which has to take in both the art and the physics. There's more to life than computer gaming, or indeed visual effects. But an understanding of physics is something which I don't think one should ever try and downplay in the school curriculum. Alex Hope's words there are really interesting ones, talking about how the visual effects rather than the computer game industry works. If you want to make computerized water believable, it needs to look and move right. It means you need to understand the science behind the way light behaves as it passes through water, partially reflected on the surface to give bright highlights, but also passing through the surface to illuminate what lies beneath, and the computational fluid dynamics that physicists use to model how liquids move. Think back to your work using Terrigen a couple of lectures ago when we were talking about images. Once you have the science, then you need to take an artistic eye to it. While the equations borrowed from physics may accurately describe how the water moves, it's not perfect, and needs a subjective and creative decision made about what feels right. Once you've created your tool, the computer to light the water realistically, you'll still need the artistic flair of a cinematographer or a painter to make it look great. At every turn, the VFX, visual effects, artist is combining maths, physics, computer science and art to create. They do this as part of a team and with a pragmatism born of a need to work to a tight deadline. What a wonderful experience. And okay, we captured a little of that, perhaps with our work in Terrigen. You can also capture a little of that in creating very, very simple computer games. I was working last year with the local TV studio on this Cracking the Code clips for the BBC as ways of looking at aspects of real-world programming and bringing them into the classroom. I'd like to show you now the clip which we put together about creating a racing car simulator.
Often computers show us a world, whether it's an imaginary world in a fantastic console game or the real world in a highly accurate racing simulator. So how do we create the virtual world? Well, we have to create a computer program that describes how everything works. I'm here with the pupils from the Ilsleys Primary School, and we're going to see if we can create a virtual car that can steer itself around a track. But first of all, we need to get a track, so let's go, guys!
To draw our track and to do our programming, we're using Scratch, a free piece of coding software. All the commands you might need are laid out on the left-hand side. You then drag commands into the middle to write your program. On the right of the screen is the stage, and this is where we're going to put our car and our track.
Great, so you've drawn your track. Now what are you doing?
Well, you have to get a new sprite, so you have to go onto the file and go to home and choose one of these.
Okay.
And then if you right-click, you can resize it.
This sprite represents the car.
Once we've loaded our sprite, we're going to need a way of steering it round our track. We can tell where the track is because it's a different colour to the background. Before we write our code, we're painting different colours on the left and right front corners of our car. We're going to use these colours in our program to try to stay on the track. We're writing a simple program using if conditions and the colours on the front of the car. If the colour on the left side of the car touches the background colour, then the program knows that the car is heading off the track onto the background. It's driving too far left, so we need to turn the car to steer back onto the track. If the colour on the right of the car touches the background, then we need to turn the other way, so we steer back onto the track.
Oh, that looks awesome. But what's the code? What are you doing?
Well, what you have to do is put these colours in. This is the background here.
Oh, okay.
And then this is my left side of the car. So if it goes close to here, it should turn 15 degrees that way.
Okay, so the lights are acting like sensors, really, which
Yeah.
help navigate the car around.
To get all the way around the track, we repeat these commands over and over again. So we've placed them inside a forever loop. In this program, we're using a variable to store the speed of our car. We can change how fast the car moves by changing the value of our variable.
What do we do now?
Well, we need to put speed in
Okay.
and set the speed to
A value.
10.
10, okay.
And then when I press the flag, it should go round.
Oh yeah. Oh.
Whoops! Looks like this car's having trouble staying on the track.
How come it's going off?
Not sure.
Should we try slower speed so we've just got a
Yeah.
bit more time to see it?
So let's try 5.
Yeah. Cool. Oh, it can handle it a bit better now.
Yeah.
Okay, that's great. Wow, that's crazy. What's happening to your car?
I don't know.
You don't know. Why don't you try changing it to a lower speed, then it may work. Okay guys, your time's up. I want to know who has the best speed. So, what did you get?
7.
7. Anyone got higher than 7?
Me.
You? What did you get, Ben?
I got 12.
12. Let's see. Oh wow, yeah you did. That's fantastic. But you do have a rather simple oval track. Do you reckon if it was a bit complicated with more twists and turns, it would still be able to go 12?
Yeah.
Yeah? I think you should give it a go. Everybody's computer model was pretty similar, but by changing a parameter such as the speed, we're able to change how things work.
I wonder if there are any other changes we could make to our program to make the car behave differently. Why doesn't our program work at high speeds? And is there a way of making it work better?
Now, for me, the really interesting thing about that is this an accurate simulation or is it a bug in the software? What you have there is a racing car which, when you're driving at a high speed, loses control and goes off the track. You could argue that that's actually a very accurate simulation. Or you could actually fess up and say, no, it's because the software isn't quite working as it should. Actually fixing that is a really interesting Scratch programming challenge, but I suspect you may have enough Scratch programming challenges of your own for me to set that as an exercise. Okay, I'm going to pull up a couple of Scratch scripts now, so just bear with me a moment. So I'm working here in BYOB, Build Your Own Block Scratch, which is the predecessor to Snap for historical reasons. I just wanted to show you what we've got going on here. We have 8 multicolored or red balls here, and we have a little script going on here. Let's see what this does. When I click on the green flag, select a random direction and keep doing something forever. Keep moving forward. If we hit the edge, bounce. And then one more thing. If we touch this red color, in other words, hit another ball, then point in a direction which is related to the one we started with. And then again, keep moving. Okay, so what you have there is an elastic or an inelastic collision with one of these objects. And all of the sprites have exactly the same script going on. Let me just make that a little bit larger. And we can then set the thing going. You're looking for collisions between. There you go, there's one there. Okay, I could watch this all day. We have a little slider here which allows us to control the speed. So which is fine. We're simulating perhaps just balls bouncing around very quickly bouncing around a billiard table. But if you've got any physics, then you'll recall Brownian motion and you'll recall the statistical model of gases and the notion that the pressure caused by a gas is in fact the molecules of the gas bouncing off the wall. We could set some counters up there to say check whether this happens, check whether that happens. And the speed here is merely increasing the temperature. And so you have one way of thinking about the relationship between the temperature of a gas and the pressure of the gas. Okay, bear with me a moment. Okay, here's another BYOB Scratch script. Have a look if you what this one does. So we click on the green flag, we go to an initial position, we set an initial couple of variables here. These are actually going to be the velocity components of this ball. So we have an initial vertical velocity and we have an initial horizontal velocity component. And again, if you've got any A-level physics, you'll recall that velocity is a vector. It's made up of its speed with a direction to it. And one way of thinking about vector is as those two components along two perpendicular axes. We clear the screen and then we've got a repeating loop here. We go again to an initial position, we display a message which says press space to start, we wait until the key is pressed. We then set the vertical velocity component up as the initial vertical velocity component, and then we repeat doing this until we either hit the bottom of the screen or the top of the screen. We pop the pen down. We set speed and direction. Speed is calculated using Pythagoras here, using as the square root of the horizontal, the square of the horizontal and the vertical component, and then the direction is simply taking the tangent of one against the other. If you've got any vector maths, you'll recognize those as resolving two components into both speed and direction. But if you've not, then please don't worry about it. We point in that direction that we just determined, and then we move according to the speed that we've set, and then decrease that vertical component of the velocity. This bit is the crucial bit, because by changing this in every click of the clock here, what we're doing is applying the law of gravity, that the acceleration acts in that vertical direction. And at minus 10 meters per second, what we're working on here is a 1/10 of a second tick rate. And so as it's in flight, gravity will be acting downwards, slowing down that vertical component of velocity. We pick the pen up when we hit the ground or hit the top, and then we suggest pressing space to reset. Okay, let's have a look at the thing. That's all very interesting, I'm sure. So green flag to reset, press space to start, and let's have a look what happens. Oh, we missed the basketball hoop. So how do you go about changing that? Well, you've got a couple of sliders here, so we could change the horizontal component. It should fly a little further now. Let's have a look at that. Press space to reset. Okay, didn't get any higher because the vertical component is still exactly the same. Let's try a little bit further on. Space to reset. Okay, that's looking good, but we need it obviously to be a bit higher up, so let's increase the vertical component. We're expecting a path somewhere like that. Okay, pathetic. Alright, perhaps too fast now there. Let's try again. Okay, and we have a winner. Okay, so I mean, it's not Angry Birds. It's much harder than Angry Birds because you're having to play with these numbers here. But a little bit of spending time with the control interface here, so that these are set by sliding back on a sprite, I think would allow you to get something which is the beginnings of a game such as Angry Birds. Okay, back to the slide deck in that case. So we've talked about, we've shown you that this is what lies at the heart of both of those scripts. The versions which you've just seen on screen are a little bit more complicated than that. But notice, please, this thing about decreasing the vertical component of velocity as how we simulate physics. Talking of simulating physics, there are some lovely programs out there. So, for instance, Numpty Physics is a free download off the internet, and what you have here is a physics simulator. If I draw a ball high up in the sky here, we've got it installed on the throwable computers. If you're in the suite and want to have a play with this. Then when I let go, physics will act on the ball, and that's going to fall down, again obeying the laws of gravity. We can move on to the next level. Okay, so this one is nicely scaffolded for us. There's a space to pause, R to reset, and it says draw a block. Gravity will act on both of these shapes. This one is going to nudge into that, and it's going to roll downhill and hit the star. So space again, and you see what happens. And that takes us on to the next level. Okay, oh, this one doesn't have quite so much scaffolding. Space, pause. If I create a ramp like that, with a little bit of luck, that's going to allow that to just roll down the ramp and hit the star. Oh, not quite what I intended, but I still moved on to the next one. So it's obviously only fixed at the 1 point. That was a surprise, as much for me as for you, I'm sure. Okay, so that's Numpty Physics. We then have much more interesting simulators. So Logo TNG is perhaps one of those things you might want to move on to once you've had the full experience of Scratch. It's another building block based programming language. I'm struggling to make it open on my computer, so I'm going to skip that bit. You're welcome to have a go with it yourself. There's some lovely tutorials out there, and do very much the same sort of thing, but again, this time using Scratch. So I wonder how many schools are preparing their pupils for the coming zombie apocalypse. Simulating the zombie apocalypse in Scratch is a thing which one can very easily do. So here we are again in BYOB Scratch. It's a very, very simple script for each of the sprites here, because I've used the build your own block functionality, which you now have, of course, in Scratch 2 as well. We click on the green flag, we run a setup script, we then do this forever, we move, we infect other sprites, and we may or may not recover. Let's just have a look at the detail of those. So let's just see what happens in the setup script here. So for each of these 10 sprites, we go to a random place. If we're below a certain threshold, then they start infected, otherwise they start healthy, and that's just setting up all of those sprites. They all run exactly the same script. By doing it as BYOB, it means that we can change build your own block. It means that you can change one of these things and apply that to all of the sprites at the same time, which saves a huge amount of frustration as you're experimenting with a program for something like this. This is called agent-based modeling, by the way. Which is what Logo TNG does very well. Let's just have a look at the moves block. Shouldn't be too difficult. Just move a number of steps, turn along a vague sort of roughly the direction you set up in. It's going to give a wobble to the walk, and if we get to the edge of the screen, just bounce around. Okay, and remember we're repeating that forever, so hence the stop block that you've got there. Infect is a little bit more interesting. Let's have a look at that. If we touch one of the already infected sprites, then switch over to the infected costume, which is of course the red costume. And finally recovery, so as to allow a little bit of interesting things happening. If we're touching orange, and the only orange on screen of course is the hospital here, then switch back to the uninfected colouring. Let's have a look what happens when we run this. Okay, so infection rate is set at 20%. We've got 10 sprites here, so 2 of those typically are going to be infected. And then they move around the screen. When one of the red hits one of the green, It's likely to turn into a zombie, become infected. It's running slow because of the screen recorder running. You sit around waiting for this to happen. Oh, so close. There. Okay. And then that infection spreads. If you've seen any of those sort of apocalyptic horror films, we've got 5 of them infected now. 1 just recovered, I think, by going to the hospital. That one's going to recover, but then get reinfected again. Don't you just hate it when that happens? We could, of course, make the model much more sophisticated by building in other properties. So, my gosh, they're all getting fairly infected now. Is there a number at which you can set the initial infection rate so that actually the population manages to survive? Or building in immunity would be another way of doing it, so that that there are people in the population who never get infected by the virus. We could play this for hours. I will stop it now, though, and return to the slide deck. Okay, so that's all very nice and interesting. That's the sort of programming which you can easily do yourself. The next thing I wanted to show you was Google Art Project. We're moving into the virtual world, the 3-dimensional experience here, rather than simulating things up on a flat screen. So let's just have a quick look at Google Art Project. Of course, Google Street View would give you much the same experience, created virtual reality models of large parts of the country. They've sent their cars around mapping taking photographs of all of the buildings which they've situated inside a 3-dimensional representation of the world. They've done the same thing, though, inside art galleries. So, for instance, here is London's National Gallery. If you get the chance next year, by the way, to do the National Gallery alternate placement, really would encourage you to take the opportunity. And we can move around the art gallery. Okay, I think I moved in exactly the... No, I was moving in the right direction. That's fine. Okay. The interface is a little bit on the clunky side. But what a brilliant way of preparing your class for a trip to the National Gallery. There we go. And some of these pictures have little labels attached, as you'll find in a real gallery, which brings up the detailed view of the image itself. We can zoom in on part of that, and you have a very high quality representation of the picture, although I'm struggling to make that work quite as... And we can explore all of the objects in that picture. So, as I say, what a wonderful opportunity to prepare children for a trip to the National Gallery. But it's not just our National Gallery that they've done this through. There's a large number of other art galleries, art collections in the world where they've got this virtual reality representation together with these very high quality, authoritative photographs of pictures together with detailed commentary about that, more details about it, all of that sort of artistic metadata stuff, and then you get some really interesting information here, and we even have a video exploring the symbolism of it. One almost thinks you don't need to go to the gallery itself. No, that would be such a shame. Google Sketchup is something which you may well meet if you take the D&T option to pair ICT with when it comes to your third year courses. And Google Sketchup is something very accessible to primary age pupils. It links also, it's called Trimble Sketchup these days. It also links well to Google Earth, so you can situate SketchUp models on Google Earth. In Switched On Computing, the commercial scheme of work I've been writing, we have this as create your own virtual art gallery. So we start by exploring what art galleries are like using Google Art Project, and then set work for, or have an activity where the children create their own artwork and then virtual gallery using Google SketchUp. I'm going to pause this and show you a recording of SketchUp in action. It's an introductory tutorial. I really encourage you to try and find a little bit of time to have a go at creating your own SketchUp model.
The first time you use Google SketchUp, there's just one thing you have to do. Click Choose Templates, make sure Architectural Design Feet and Inches is selected, and click Start Using SketchUp. First things first, a quick tour. Up here at the top of the screen, these are your tools. Right here in the middle, this is the modeling window. This is Sang, he's in every new model you make. And down here at the bottom, you've got information about the tools when you use them to make models in SketchUp. Okay, let's dive right in. I'm going to use the rectangle tool to draw a rectangle on the ground. I just clicked once on the left and once on the right. Now we've got Sang standing in the middle of a rectangle. I'd like to turn the rectangle into a box, so I'm going to take the push-pull tool, looks kind of like a brown box with a red arrow coming out of the top, to click once on the rectangle and pull it up right around Sang. Now, I want to take this 3D box that I made and spin it around, so I'm going to use the orbit tool. Looks like two blue arrows forming a ball. And when I click down and move my mouse around, you'll see that I can spin this thing around in 3D space. That's called orbiting. I'm going to take the rectangle and cut a door in the side of this building, just like that. And then I'm going to take the push-pull tool and push in that a little bit. I'm going to take the eraser and erase away the bottom edge of the door. And what you'll see when I get the orbit tool again is that Sang's actually still inside. So what we've got is a little building with Sang inside. Next thing I'm going to do is take the circle. Let's draw a little circular window on the side of the building right there. Let's do another one over on this side of the building, just like this. And what I'm going to do in this case is actually use the select tool to select the circle that I drew and then press the delete key on my keyboard. And I'm going to do the same thing over here. Select and delete. And when I go up and get the orbit tool, you'll see what happens. See? I've cut holes in the side of the building, just like that. Next thing I'm going to do is zoom out a little bit. This little magnifying glass up here is the zoom tool. Let's just zoom back. And I'm going to put a roof on this building. And the easiest way to do that, if you're new to SketchUp, is to use the push-pull tool right there. Click once on the roof and bring this up much taller than it was before. And then, let's see, I'm going to get the orbit tool. Let's bring that up. I'm going to kind of spin this thing around so I can see this end of the building a little better. And I'm going to take the line tool, looks like a little red pencil, click once on the top edge of my building, once down there, and then I'm going to click again where I clicked before, and then click down here. And then I'm going to use the orbit tool to orbit down. Let's get the push-pull tool, click once on that triangle that I just made, push that back, orbit around, use the push-pull tool, let's push that back as well, and use the orbit tool to see what we've made. So now we've got Sang inside a little building with a rectangular door, two circular windows, and a peaked roof. I think the next thing we need to do is add some materials. So I'm going to go back to my select tool. That's a good neutral tool to go back to when you're not doing anything. And I'm going to go to the window menu and choose materials. Now, I'm in my little roofing materials palette here, but I'm going to click here and go up and look for brick. Now, just take that first brick texture, and my tool automatically turns into the paint bucket tool, which is up here. But when you click a texture, it automatically turns into the paint bucket. And I'm going to just click where I want to paint brick. So click there. Now, if I want to paint the other two sides of the house, I'm going to use the orbit tool to just sort of spin myself around. Let's go back up to the paint bucket, click and click. And I want to choose some, I think some nice shingles for the roof. So let's click on some shingles, click there. Let's get that orbit tool to just spin ourselves around again. Back to the paint bucket, click there. And what we've got now is a little building with Sang and brick and a little roof made out of shingles. And it looks pretty good right now. I'm going to close up my materials palette and go to Window and Components. Now, the Components dialog box, or browser, is where you go to find things like furniture and cars and trees and those kinds of things. What I want to do is bring in a piece of furniture for this little house. And right here I have a bench. I'm going to click on the bench, and then you'll see it goes on the end of my cursor. I'm just going to set it down exactly where I want it to be. And I think this model needs one more thing, and I think that's probably a friend for Sang. So I think I remember up here seeing, yep, there she is. Right here, Nancy. I'm going to click on her, and you'll see that Nancy's at the end of my cursor now. Let's just put Nancy over here in the model. And you could just drag in anything you like from here. You can type in what you're looking for right here, and this little button actually gives you access to even more libraries of components. So there's a whole world of content in here if you like. For now, I'm going to close that up. I'm going to get my orbit tool to take a look at what I've got. And, well, at this point, actually, I'd like to show you something that actually really just advanced users of SketchUp use, but I think you'll get a kick out of it. So watch this. I'm going to go to Window, and I'm going to turn on Shadows. and the little shadows dialog box opens. Now if I click display shadows right there, and then I move the time slider back and forth, you see how the shadows are moving? I'm going to move the date slider as well. And that's because these two sliders are controlling the position of the sun in SketchUp, which changes the shape and the position of the shadows. And one of the things I realize is that Nancy over here is standing in the sun. So I think what I need to do is make something that'll provide her some shade. So I'm going to go up here to the Orbit tool. Let's go and use the rectangle. Let's just kind of draw a little rectangle on the side of the building, and I'm going to use push-pull again. Let's click once, and then I'm just going to pull this out so that it's on top of Nancy. I think I'm going to add a little support. That's funny that that's brick, because they don't usually make overhangs out of brick like that, but this isn't real, so I don't have to worry about it. Let's just use the circle to draw a circle on the underside there. I'm going to use the push-pull tool, click on the circle, and then hover on the bottom of the house and click, and then use the Orbit tool. And you'll see what that did was make sure that that column, this one here that I just made, comes down all the way to the ground. Now, it looks like Nancy's still in the sun, so I need to move this time of day around and the date until Nancy's not standing in the sun anymore. There we go. Cool. So now Nancy's in the shade. Sang's inside the house. They've got a little bench to sit on, and I think everything's pretty good. All right, that's all I'm going to show you. It's your turn. You can model a house for Sang or anything else you can imagine. Thanks very much for watching.
Taking that a stage further, and you can make these things interactive. And Minecraft has really captured the imagination of many, many teachers. Now, not to mention school children. And they're setting up a Minecraft server, creating a virtual space in Minecraft for your pupils to go in and create things, to make models. There's a lot of the sort of modelling of reality, of making things to show to other people, of solving problems. There are also links, if you look for them, with the design and technology curriculum and the science curriculum. I'll show you a short clip from a video about this for a primary school in Brighton now.
Okay, it's a quick tour of one of our students' houses today, and she's made a lovely job of this. Really, really great, really nice choice of materials. There's a beautiful purple carpet. I'm not sure if you can see the purple on the iPhone very well. A nice bed and some windows so she can see monsters coming. Really, really lovely work. And it's got a glass roof to let all the sun in. And a lovely, lovely bookcase. She's created it with a front door so it's secure. And she told me she chose the pumpkin patch as well, just because she liked the look of the neighbourhood. So some really good choices there. Really pleased with that work. Just 50 minutes today they had, and she just found a really beautiful place, a nice little jungle in a pumpkin patch, and then built a nice, beautifully aesthetically designed building with a few mod cons with a bed and a bookcase. Beautiful work, really nice, really pleased. Tell me more about it, Jules.
Well, basically it's got loads of torches at the front to keep zombies away.
Torches at the front to keep the zombies away. Excellent.
And Minecraft is also available on the Raspberry Pi if you've been wondering what you could do with one of these funny little £25 computers. The really interesting thing about the Pi edition of Minecraft is that it is programmable, not, alas, in a lovely block-based language such as Scratch, but using a Python-like language. What we have here is, in fact, the wrong image, but for x between 0 and 10, or 1 and 10, sorry, 0 and 9, and for y in the range 0 to 9, then put a block in place there. So this is a script written in Python to create a 10 by 10 wall in Minecraft, which I think Minecraft users or players in the room, I hope, will find reasonably interesting. And there are some really interesting anecdotal stories of how much children learn through playing these sorts of games and how they go about learning. This is Will Richardson writing about his own son. When he's not at school, at least, I looked at how he's learned Minecraft. Totally understand why school is becoming more of a struggle for him. First, he's a passion for learning the game. That's crucial. He creates his own constantly updated curriculum based on what he knows and needs to know next. He cobbles together his own multimedia text using YouTube videos. He finds his own teachers, local and global. He's engaged in assessing his own work, scrapping it, starting over when something fails, building or refining when he gets new ideas, offering feedback to his peers on a regular basis. You'll see this too, of course, with the Scratch online community of children interacting with one another as they make better and better Scratch scripts. Contrast that, though, with how his study might look in the classroom, operating under the assumption that Minecraft content and coaches are scarce. Receive the same text as everyone else, be assigned the same reading at the same pace, be asked to achieve the same goals in the same way as all other students, and then be assessed in ways that would likely tell us little about how he has developed as a learner. I think there may be a hint there of the way which we might see Scratch programming being taught in school, rather than the sort of lovely organic approach that we see there when young people are using it outside of the school curriculum. That was pretty much it, really. Hopefully that's been interesting and useful. I would really encourage you to have a go with Trimble Sketchup, which we've got installed on the machines in Frobel Labs, and it's a free download off the internet to create your own virtual reality model and add that up onto a blog post. If you've got time, then do have a look at Logo TNG. Sorry I couldn't get it working in the demo here, or Sketchup, or Minecraft if you'd like, and explore those platforms for yourself. Okay, I'll be back in next Friday and we'll be having a look then at some of the robotics stuff.